in the last class. We were looking at the Fourier series, and we looked at how the Fourier series comes about, in some sense at least. And we looked at a couple of examples. So one was the sawtooth wave. This is an odd function, which means that the cosine terms are not going to be available to us. So for the odd function, you have got fx equal to only bn sine n pi x by L, and you can do this algebra and we are going to get the bn's. Okay, this we did. Then we looked at a couple of examples of even functions. So I've got fx equal to x square is an even function, and for an even function now the cosine terms are going to be surviving, and therefore the a0 term also is going to be surviving. So we computed the a0 term and then the an's were computed. And the last example we took was some other wave, maybe it's a sawtooth wave or whatever it is, a triangle wave, whatever you may want to call it. And here also only the cosine terms are going to be surviving. And then we said that there are so-called Fourier sine series and Fourier cosine series. And if we have got a function, and what you see in blue there is the given function, and this given function, for whatever reason you want to represent it as a sum of sines and cosines, then there are several options that are available to you. So this guy is like this, and this is what you want to, let us say, model for whatever may be the reason. And you can either say that I would like to see a periodic function, and what we have seen is period always from minus L to L. This is what we are comfortable with, although not necessary to do so. So this guy, I can just extend this guy, this dotted line, and then now I can say that this is going to be an even function, because this guy is just the mirror image of the given function. Okay, so that's an even function. And you can also say that I'm going to model this like this, which is going to be making it an odd function. So that's what's given in green up there. So blue is the one which we are trying to model somehow. The purple one is the first one, which we are going to make it into an even function. And then you take the green guy, that's going to give you an odd function. And if you don't like either even or odd functions, you can just say that I'm going to just use this guy here. And I'm going to say that this guy is L, but this is 2L. Okay, so that's twice the period, and I can go ahead and formulate it in that fashion also. The only thing you need to remember is that whichever way you are going to make this into an odd function or an even function, suppose you do this, okay, so that's fine. But if you are going to then now want to find out what is happening at some other location, that is going to be dependent on how you have modeled this guy. Okay, so this guy is going to look something like this. Okay, so this guy, so this is the coupon which repeats itself. So this coupon repeats, this coupon keeps on repeating itself, and if for whatever reason you wanted the value at this point, okay, and not at this location, then the expansion is going to give you this value here, which is this guy here. Similarly, if you're going to now model this guy like so, which you can do, It's up to you how you do these things. And so this guy now is going to look like so. So this guy is going, so this is the coupon which repeats itself. So this is L, this is minus L. So this is the whole period, and this whole guy repeats itself. Remember, we have said that we are talking about 2 pi periodic functions, okay, or 2L periodic functions. So if now you went ahead and just plugged in this number, then you will get this guy here. Okay. And if you are going to model this just the way it is, then you are going to get this guy here. Okay. So this very same guy is likely to give you different values within this function of interest. All these models are going to give you the same number. But if you are going to be looking at something that is outside of this domain, then you need to be careful about what you are talking about. Okay, so depending on what you are trying to model, how you are trying to model, these things are going to give you different results. Just for the heck of it, if we are interested in the point there, okay, at this particular location, this particular model is going to give you the average of these two, which is going to be here. The other model, which is like so, is going to converge to this point here, and the other model, which was like this, is going to converge to that point there. So all these functions are going to converge to different points at this particular interface. If that's of importance to you, then you must be careful how you are modeling these functions. Alright, so then we said that if you have got a periodic function as the right hand side of a differential equation, which we never talked about when we were talking about the differential equations with non-homogeneities. If the right hand side is a periodic function, then you can go ahead and model it in an appropriate fashion using the Fourier series. And this was the example for a random right hand side that we had. So you have to go ahead and do the algebra, except that for each of these particular terms on the right hand side, you are going to be getting a particular, this is the undetermined coefficient approach that is being shown here, but you can use any of these approaches to go ahead and get a solution. So this is where we quit when we were looking at the Fourier series before midsem. Okay. So we continue on this business of the Fourier series now, and before midsem we spent a reasonable amount of time. We don't need to now spend so much time on trying to understand what these terms mean. We have said that the Fourier series is going to be comprised of a series of sines and cosines, and what we said was that these components of the Fourier series are nothing but some kind of a projection of that function onto the basis functions. Okay, so that's the basic philosophy that we had used when we were looking at the Fourier series, and therefore we came up with a bunch of basis functions. We didn't come up with that, we just borrowed it from mathematics. So we said sines and cosines from trig are the functions that are going to be useful to us, and we said that we need orthonormal functions. So the orthonormal functions are what we are looking at when we are looking for basis functions, just because they are convenient to us. That's all it is, nothing more than that. You are welcome to use other functions also. Okay. But what we did not show is that these are a complete set of basis functions, in the sense that any function is going to be representable if we have just these basis functions. Okay. That's something which is probably heavy duty math, which I myself am not aware of. The mathematicians have taken care of that. Okay. So now we just say that there is another methodology which is the same Fourier series, but we are going to use the complex form of the Fourier series, and this guy happens to be more convenient for programming, and therefore we look at it even though we have kind of understood the sine and cosine part. And most of these softwares that you will see will always spit out the complex form of the Fourier series. Okay, so before we go ahead and start, once again just a couple of definitions so that we are clear about what is being talked about. We have said that we need the magnitude of a function, and for a vector, once again we said that V transpose V is going to give me what is going to be the magnitude of the vector. Okay. So if I've got a vector V, then the magnitude of the vector, this is something that we have seen in the past, okay, or you have seen in the past several times. Okay. Now, if I have got a complex vector, then the definition is, if this guy is a complex vector, then the definition of this guy is V transpose square root of. Okay. So, if V happens to be a complex number, then we say that you are going to get the magnitude of the vector by saying I have got V transpose times V transpose times V of the complex conjugate of that particular vector. Okay. This is just once again a definition which is nice to use, essentially so that we are kind of consistent with our definitions. So let us just take a simple vector 1 1. This is a vector, and in my 2D space this guy is going to look something like that. Okay. And the magnitude of this guy, this is 1i, this is 1j, and this is root 2. And if we look at our definition, we are going to just say that the magnitude of this guy is going to be square root of V transpose 1 1 and 1 1, which you get as root 2, not an issue. Now suppose V is a complex function. Suppose V is a complex function, and let me now say that a simple complex function, we make it I and I. Now what happens to this guy here now? What is this definition going to give me? 1i, this is the transpose of the vector V. So V is equal to, we have said is 1i. That's my vector V, and if I want the magnitude, and if I look at the same definition that I had earlier, which is V transpose V, what will I get here? What will be this number here? 0, correct. This guy comes out as 0. Okay. And the way we normally are going to represent this on the complex plane, usually, we have the real axis, we have the imaginary axis, this guy, this is how we represent it usually. This is the real guy, this is the imaginary guy. So this guy is 1 plus I, and the magnitude is again root 2. So you change this definition so that we are in line with our representation of complex numbers, and say that I am going to call this magnitude as V transpose and then V complex conjugate of that vector. So that's my definition. Okay. There is just some kind of consistency has to be there, and therefore the magnitude of a vector is going to be V transpose times the vector complex conjugate. So that's a definition. We keep that in mind. Okay. So now we go ahead and say that earlier on we have said that our Fourier series had got a set of functions which were orthonormal. So these were orthonormal functions, and we, from trigonometry, we had identified that cosines and sines are orthonormal functions. And we have this very nice expression, e to the power I n pi x by L is cos n pi x by L plus I sine n pi x by L. This also we know. So because sines and cosines were orthogonal to each other, it stands to reason that maybe this guy also is going to be orthogonal to each other. So you say that I'm going to hypothesize that maybe because earlier on my basis functions were sines and cosines, maybe these guys also are going to give me some kind of orthonormal functions. Okay, so which means that I'm going to say e to the power of minus I n pi x by L da 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 da, e to the power of minus I pi x by L, then maybe some constant e to the power I pi x by L, and then e to the power of n times I. So these we can claim to be the basis functions, okay, in the complex plane. So in the complex plane, we are going to claim, or we are going to try to see if these are going to be my basis functions. Maybe they will be, because we have already seen that sines and cosines are the basis functions, and therefore these are also basis functions. Okay, just like we have said that the definition of the magnitude of a complex vector is slightly different from the other definition that we are used to seeing, we also need to have a definition for the inner product now. Okay. Remember, we are once again now, sines and cosines are 2 pi periodic functions. So we are looking at 2 pi periodic functions. Okay. So these are all 2 pi periodic functions. So for 2 pi periodic functions, let me just say that the inner product of f and g, where these guys now are complex numbers or complex functions, if you will, the definition is going to be 1 by 2 pi minus pi to pi f g star dx. This is my definition. Earlier on, we said that the definition of the inner product of two functions was 1 by pi minus pi to pi f g dx. Okay, that was the basis for us to build up the rest of the case. Okay. Now we are saying that the inner product of two functions is going to be defined like this. Once we have a definition, we have to stick to the definition. Okay. So we don't change the definition once we have made a definition. So this is the inner product definition that we are going to be using. Alright, good. So let us go ahead and now we want orthonormal functions. So what was my definition of orthonormality? What are orthonormal functions? Physically, whether they make sense or not, we are not concerned. What were orthonormal functions? The inner product is 0. So the inner product of the functions is 0 and the inner product with itself is unity. Okay. So the inner product with itself is unity and the inner product with any other so-called basis function is going to be equal to 0. So that qualifies for being an orthonormal function. So let's just see if these guys are orthonormal. You may not remember, but when we were talking about sines and cosines, at that time I said that I'm not going to be able to show this on the board because It's something which is extremely messy from a trigonometric point of view, but for these functions it is fairly easy for me to do, so I will do that. Easy stuff I do, difficult stuff I leave it for you guys. Okay, so we are wanting to look at, let us say, e to the power of I n pi x by L and e to the power of I m pi x by L. Okay. So what's going to be the inner product of these two guys? I n pi x by L e to the power of I m pi x by L equal to, my definition was there, 1 by 2 pi integral minus pi to pi. What should I put here? E to the power of I n pi x by L, and then what should I put here? E to the power minus I m pi x by L dx. This is my definition. Okay, we have said that I'm going to have my definition of the inner product of two complex functions as 1 by 2 pi minus pi to pi e to the I and then the complex conjugate of the other function. Okay, now it's just brute force algebra. So I've got e to the power, so this inner product is going to be 1 by 2 pi, and then you perform the integration, it is e to the power of I n minus m pi by L upon, e to the power I n minus upon I n minus m pi by L. Okay. And this x, and from minus pi to plus pi. Right. So I just have integrated it, nothing else. Okay. The next step, I think I'll use my slide there. So if I'm going to get my inner product, I'm going to take this like this, and for 1 minute let us say that n is not equal to m. So if n is not equal to m, this guy is going to survive, and I will again use my definition of e to the power of I theta to be equal to cos theta plus I sin theta, and then you get that particular expression there. Okay. So this guy now, I'm going to just use that, and all of this, let me just erase, the algebra is out there. What you end up with now is twice I sine of n minus m pi upon n minus m I. Okay, so this is what I'm getting. So what is that expression here? What is sine of n minus m pi always? It's always 0, right? So therefore this guy becomes equal to 0. Okay. What does that mean? The inner product is 0 means it is orthogonal. Okay. So e to the power of I nx and e to the power of I mx are both orthogonal functions. Okay. I want orthonormal functions, right? So how should I check whether it's orthonormal or not? N equal to m. So if I put n equal to m there, you can easily see that e to the power of in, e to the power of minus in is going to be equal to 1, and then 1 by 2 pi integral minus pi to pi, 1 is going to be equal to 1. Now, what did we get when we had sines and cosines? What did we get when we had sines and cosines? Same thing, right? The sine and cosine was equal to 1 when my 1 by 2 pi was replaced with 1 by pi. Okay, so that was the definition. Okay, so the definition has ensured that e to the power of I nx, e to the power of I mx are orthonormal functions. Great. So we have these functions. Okay, even if it is minus I n x, minus I m x, it's not going to change. The algebra remains the same. Okay. What about now the constant? Remember that we had sines, we had cosines, and then what was the constant we had? It was not 1, but it was 1 by root 2. Okay. So that the functions are orthonormal. Okay. Let's see what happens in this particular case. What happens in this particular case? All of these guys are fine, and now what I want is the inner product of some constant c with e to the power of I m pi x by L. Okay. So e to the power of, remember that we have got this guy here and we have got this guy here, and okay, what is it that I am going to get from here? What is the inner product of this? Integral of this guy 1 by pi minus pi to pi is going to be equal to 0, right? So this is fine. The orthogonality is taken care of. What is c comma c? What is c comma c? This is integral of minus pi to pi. What's inside the bracket? C into, but c is a constant, right? It's a real constant. So this is c into c, correct? And I have got 1 by 2 pi here. Okay. So this guy becomes 2 pi, this guy becomes equal to 1. So c, I'm going to use equal to 1. Okay. So 1 is going to be something that is going to be another one of the basis functions, unlike, remember when we had 1 comma 1, then we had a 1 by root 2 here, right, because this 2 was not there. Okay. So this definition now has given us the basis functions which are going to be e to the power of I m pi x by L da 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 1, and then e to the power of I n pi x by L. These are now my basis functions in the complex plane, okay, which are, what qualifies for a basis function? Orthogonality and normality. Okay. So each of these guys is orthogonal with respect to another guy, and they are normal with respect to each other in the sense that the magnitude is equal to unity. So these are my functions which I'm going to say are going to be the basis functions, just like we had the sines and cosines. When we had sines and cosines, the big difference was this guy was 1 by root 2. That was the only difference. Okay. Now you are ready to go ahead and say that I'm going to create now my fx. Fx is going to be equal to summation of now, right? Remember we said that you have a function, you project it onto the basis functions, and whatever you get times the particular function is going to be my 1 to infinity minus plus some constant which is c naught plus this is going to 1 to infinity Cn e to the I n pi x by n. So this is the Fourier series parallel of, or the complex form of the trig series that we have already seen in the past. Okay. So I've got fx equal to c minus n e to the minus I n pi x by L, some constant in between, and then e to the power of I n x n pi x by L. Okay. You can always write this guy as minus infinity to plus infinity and all kinds of formulations, but basically what we are saying is I've got this as once this and this for along with unity form a set of basis functions so that I can represent this function f of x. Okay, so I want to do a little more algebra. Just because we want to appreciate something else here. The series which is there is e to the power of I n pi x by L plus C naught plus that. I don't want to write the step in between, it's longish, but it's nothing very profound up there. All I am doing there is to expand my e to the power of minus I n pi x by L as cos n pi x by L minus I sin n pi x by L, and then the next term is being expanded as cos n pi x by L plus I sin n pi x by L. But the next step which is there, which is the final step, let us just write down. So f of x is equal to now summation of cos n pi x by L multiplied by Cn plus C minus n plus a C naught plus summation of sine of n pi x by L Cn minus C minus n. Okay, and this goes from 1 to infinity, this goes from 1 to infinity, and there is an I sitting in here. Okay, this is just the same series written up in terms of sines and cosines. Okay. Now what can I say about this guy here? Okay. Now first question is, should this Cx, should this Fx collapse to that sine and cosine that we had? Should it collapse to the same thing or not? I have function Fx is not changing, right? The sines and cosines are there, right? So therefore this representation should be identical to the previous representation that I had, right? There's no reason why it should not be. And therefore, what should I do? Is this a complex number or a real number? Cn. What is Cn? In here, what is this Cn? Cn, what is Cn? Cn is equal to integral of what? Fx times e to the minus I n pi x by L. Okay, 1 by 2L minus L to L. Okay, so in general, this guy is a complex number, right? So do you expect this to be complex or just a simple real number? In general, it is a complex number, right? So in general, this guy is a complex number. All right. Now, am I interested in real signals or in imaginary functions? Usually in real functions. Okay. So if this guy is a real guy, on the right hand side I have got complex guys, right? So what is the way out? Pardon me, conjugate, correct? So how to make sense out of this right hand side, which is a complex number, so-called complex, in the wake of the fact that this guy is a real function. Now, is this real? This guy is real. The only place where I can play around with is to see if I can make this guy into a real guy. I want to make this real, I want to make this real. So what is the way out? This can happen if Cn is what? What is Cn? I'm just saying you just want to make this whole thing real, that's all you want to do. I've got, let us say Cn is A plus Ib. Okay, Cn is A plus Ib. I have got Cn plus C minus n. Okay. If Cn is A plus Ib and I want this guy to be real, what should C minus n be? A minus Ib. Okay. So C minus n should be A minus Ib. Fx is a real function and we have done some crazy stuff and we have come up with something which said fx is going to be a complex function, but that's not acceptable to us. Okay. So fx cannot be a complex function and therefore what we say is I have got this Cn here, these two are added together, these two guys are subtracted together. So let me just hypothesize that Cn must be equal to the complex conjugate of this if fx is a real function. Okay. If all our algebra is correct, then that will happen. Okay. So this guy is A plus Ib plus A minus Ib. Okay. So therefore these two guys will go away and what you are left with is 2A. Let me just get rid of this now. This is 2A, where A is some real number. Okay. Similarly, what is going to happen here? What will happen here? Cn minus C minus n. This is 2Ib. Okay. And what is I square? It is a minus 1, right? Now, does that look like the Fourier series that we always have seen? This is exactly the same as what we had. 2a cos something, some constant, sine something, the negative sign we will worry about later on, but otherwise there is a constant, there is a cosine, there is a sine. So we will see later on in the next class that all these computer software which are going to spit out the Fourier transforms and the coefficients always spit out these numbers and they are always complex conjugates. This is what, because you are trying to go ahead and get the Fourier series in the complex form, and because I have got my fx as being a real function, this is a necessary condition, which is Cn is equal to C minus n complex conjugate. Okay. That's all we need to understand as far as the complex Fourier series is concerned. Let's take an example so that we are clear about it. Okay, so this is the same example that we had in the past, okay, which we have worked out based on the earlier definition of my Fourier series, which is I have got a function which is an odd function. We did several examples. Okay. So this guy is 1, this is 1, this is 1. Okay, so I have got a square wave in some sense, and the red guy is the wave that is there, and this is plus L, this is minus L. Okay, now will C not survive or it will not survive? Will C0 exist? It will not exist because it's an odd function. Odd function, the constant term is going to go away because you are integrating fx, and this is an odd function, so this and this will cancel out. Okay. So the C0 term is not going to be there. So it's been done there. Now Cn we said that the definition of Cn is 1 by 2l minus L to L f of x e to the power minus I n pi x by L dx. Okay, so this is my Cn. Okay, so you can go ahead and do the algebra, right? That you can do. All the details are there. So Cn, if you go ahead and do this, all that you need to do is to go from -1 to 1, and then I'll just put the things, that's all. -1 to 1 and f of x, and so you go from -1 to 0 and then plus 0 to 1, and here it is 1 times e to the power dot dot dot, and this is -1, this is +1 e to the power dot dot, and you go ahead and perform the algebra, and when you do the algebra you get the following. So trust me, the algebra is correct. This is 1 by pi and 1 minus e to the minus I n pi x by L upon I n. So this is going to be my Cn. So you can go ahead and check the algebra. The only thing now I want to show you is the previous time when we did the same example. I'll just put that up. This was the previous example, same thing that we did. So in the last class we had done the algebra in more detail, but that was the first time we were doing it, so we did the steps. Now we just say that, but finally the solution there, okay, it looks kind of different from what is here, right? Should it be the same? It should be the same, right? If the function is the same, there's no reason why the solution should be different, right? Okay, so what is it that is going to happen here therefore? So let us see what this Cn is going to come out as. So this Cn, unfortunately I don't have the algebra, so we'll have to just quickly do it. So this guy here, okay, so I've got 1 by pi, okay, 1 by in, okay, and should this Cn be a complex number or a real number? Should this Cn be complex or should it be real? Generally it is complex. In general it is complex. In this case, do you expect it to be a pure complex number in the sense that the real part is 0 or not? Okay, look at this guy here. Okay, I've got that expression right there. Okay, I've got an odd function. What happens with an odd function? Do you get the cosines or do you get the sines? When you're going to expand a function, an odd function, do you have sines surviving or the cosines surviving? Only the sines surviving, right? Which means that that first term should go away, right? So the first term should not be there, correct? Which means that the first term has got a pure real number. This one is pure imaginary. We have already said that Cn is a plus ib, c minus. Therefore, what we should be ending up for Cn, if our algebra is correct, is a pure imaginary number. Okay. All right. That's one thing we have to notice. It doesn't look like it, but it actually is. Okay. So this is 1. What is e to the power of? What is e to the minus I n pi? Cos of n pi minus I sine n pi, right? I've just expanded it, nothing else. What is sine of n pi? 0, right? So this guy is gone. So now it starts to appear like maybe the algebra is correct, right? I've got 1 minus and then I've got an I sitting in here. This makes it a purely imaginary number, right? I multiply and divide by I get a minus I here. Okay. Okay, so I have got an I 1 minus cos of n pi and this is my Cn. Okay, now what else has to be done? Cn minus minus Cn. What is that? Cn is I minus minus I has made it a 2I, right? So I am going to get a 2 sitting in there. Okay, and I have to throw this I out, and then if I now compare this expression with what I had in the past, you will find that they are the same. So I had a 2 by n pi, 1 minus. So this is from the real place. So 2 by n pi, 1 minus cos n pi, and then of course that sine n pi is the function, the basis function that is multiplying it. So what we are saying is that everything that you are going to be doing in the complex domain and the real domain will kind of come out to be the same thing. So you are welcome to use either the complex formulation or the real formulation. Either you use sines and cosines or you are going to be using this type of a formulation. So this anyway I will add as a home assignment so that you actually go ahead and do the algebra and ensure or convince yourself that this and whatever we were talking about. So this guy and the one previous is going to come out to be the same. We have shown this. I have done it in a kind of a loose, hurried manner, but you can do the algebra properly and show for yourself that the two formulations give you exactly the same numbers. Okay. All right. So there are some other issues associated with it, which we will see slightly later. So as of now, let us say that we understand this business of the Fourier series. Okay. What we have said is, I've got a function and I am expanding it either in terms of sines and cosines or in terms of some imaginary functions. So that's basically what we have been doing. Okay. Now we look at something called the Fourier transform. Essentially it emerges from the series. So what is this guy called the Fourier transform? So we try to understand something called the Fourier transform. So the first thing that we say is, I've got a function which is looking like so. Some function is there like this. Okay. And we can go ahead and represent it as a Fourier series. Fine. Now, if I'm interested in what is the Cn's in here, remember there is a Cn and there is the basis function. Okay. So the Cn is in some kind of sense, if you look at the length as time, it's some kind of a frequency, but whatever it is, if we are interested in the Cn's that are going to be forming up this particular signal, then we need to do something else. So first let us say that I've got a function like this, and how do I represent this function as a Fourier series? What can I do? I want to represent this function. This does not look like a periodic function, right? but I would like to force it to become a periodic function. I'm only interested in this region here. Let us say this is L or 2L or whatever. What can I do? And I am a fan of Fourier series. I want to represent this guy as a Fourier series. What can I do? Is this periodic? This is not periodic, right? But the same thing which we did in the past, which is we said that we had this function here, correct? And we wanted to somehow represent this function. And what did we do? We made it, we brute force made it periodic, correct? And so this was periodic. I could do this, I could do this, I could do this, I could do anything to make it periodic. I'll do the same thing here. I can make this periodic by saying that I'm going to have dummy signals here. Correct? All these are dummies. This dummy could be like this also. No problem. So I'm going to create dummy signals so that I can represent this guy as a Fourier series. Okay. Now the other thing is, I have got this term called n pi x by L. Okay. Now n is what? N is a number. Can be 0, 1, 2, 3, 4, 5, 6. Right? So if this n is 1, 2, 3, 4, 5, 6. Right? So what is it that I'm going to be getting as some kind of a frequency? What is the frequency? 1 by L or pi by L. Okay. So if my L can be increased, then this number becomes smaller and I can have a large number of more frequencies. Okay. We'll understand this a little bit because we are going to do this quite a few times now. Okay. So what is the way of increasing this L and not changing the signal? How can I do that? How can I increase the L? Because let me just say that my aim is to increase this L. I want to increase this L somehow. But I want to keep this signal the same. What do? I can just say that instead of making this dummy, right, I will say that I will take an extended part of this. It is 0. Doesn't matter. This is my periodic signal. The periodic signal now goes to L here. Why do we want to do this? We want to do this so that, because n is a digital number, 0, 1, 2, 3, 4, 5, 6, correct? So if I want a larger number of these n's inside a given value of L, correct? I would like to have more of these guys, so I'm going to increase this guy in this direction and this guy in this direction. And what is the limit? Okay, so suppose this is this, then my frequency, my signal is going to be looking like, now let me just not do that. Suppose I've got this and this is my, I have made this my L. So then my signal is going to be looking something like that. Something like that. Okay. So this is now my period. This is now my period. I want this L to be as large as possible. So what is the largest L that I can think of? What is the largest L that I can think of? Infinite. Okay. So what we say, okay, I think we stop here. I'll see you again tomorrow. Thank you very much.